This lecture is on Chapter 9 on gases. I'm not going to spend a lot of time on the first section. We'll focus in this chapter on being able to use the different gas law equations and formulas to solve problems. But this first gives you an introduction to gases, and this just shows the composition of dry air at sea level. A gas is a large collection of particles. They move at random through a volume. It's primarily empty space, and it's those collisions of the particles against the walls that exert a force, and this is what we know of as pressure. There are different ways that we can measure pressure. This is one way in a mercury-filled dish. Sort of defines what we refer of as atmospheric pressure. This is an important slide. So pressure is equal to force per unit area. The conversions that you see below are ones that you should probably write down on your exam sheet, or at least have available, or you could, I suppose, memorize them. The ones we use most often are the first two, that 1 atmosphere is equal to 760 millimeters of mercury, and that comes from this previous slide, this example of using a mercury-filled dish. We know that in atmospheric pressure, the column rises to 760 millimeters, so that's where we get that from. 1 torr is equal to 1 millimeter of mercury. 1 bar is equal to 1 times 10 to the 5th pascals, and 1 atmosphere is equal to 101,325 pascals. So again, I would write these down, have these available for you. The first one is the one that I think you'll find we use most often. We can also use open-end manometers, shown here, to measure pressures. I'm not just going to skip through that, but this is just one way that we can measure pressure. Okay, so right to the gas law equations. We'll first go through the relationships between sort of two variables holding the other two constant. You'll see what those are, and then we'll combine them all together into the ideal gas law equation. So we can define different physical properties of a gas: pressure, temperature, volume, and number of moles. These are the 4 that you'll be using most often. And we can also determine the density. So we will there's a problem in your text that walks through that as well. So the first law is Boyle's law. This says that volume and pressure are inversely proportional to each other if you hold the number of moles and temperature constant. So if, for example, you in the figure that's shown there, the column on the left has a pressure of 1 atmosphere, and you can see that the volume of the gas is 1 liter. If we double the amount of pressure, so to 2 atmospheres, you can see that the volume decreases by half. So there's an inverse relationship here between volume and pressure. This is known as Boyle's law. In terms of using this in a calculation, we use the formula seen on the very bottom here, and that is P initial times V initial equals P final, V final. And so you could be given initial states and a final pressure, for example, and be asked to calculate a final volume. So in all of these types of problems, just like you've been doing all along, you're given all but one unknown that you need to solve for. So when approaching these problems, the first thing to do is to figure out which type of gas law equation it is. So figure out what are the things that are varying, what are being held constant, and then use the appropriate law and relationship to solve. I find it sometimes helpful for students when you're writing these equations down to put, say, Boyle's law next to it, and the fact that pressure and volume are inversely proportional, if that's helpful for you in terms of visualizing where we get this equation from. But so there's your first equation that you can use relating pressure and volume, and that's Boyle's law. Charles's law compares volume and temperature. So we know that volume and temperature of a gas, when we hold constant pressure and constant number of moles, is proportional to each other. And on the bottom here is that relationship expressed in a mathematical equation that you can use. So V initial divided by T initial equals V final divided by T final. Again, another equation to make sure you have written down and know how to use. And again, in these kinds of equations, the way that it's set up is you'll see you'll be given an initial volume and an initial temperature, maybe a final volume, and it will ask for the final temperature. So there are several examples in the text that are given to you, several worked examples, and examples examples at the end of the chapter too. Avogadro's law relates volume and number of moles. So if we hold temperature and pressure constant, volume and number of moles are proportional. And so it's not written on this slide, but here are those three. So Avogadro's law, that formula would be that V initial divided by the number of moles initial is equal to V final divided by the final number of moles. So these are definitely three very important relationships to have written down and know how to use. And you will see problems on these on the pre-class and the homework and obviously on the exam. So we have these sort of separate relationships here. In each of these cases, the two other variables being held constant in each case. So the question arises, is there a way that we can include all four variables together so that we could come up with a way to talk about a gas with all of those variables? And so that is this sense of an ideal gas law. And without going through the derivation here, we end up with the ideal gas law. It shows those relationships. And the R is we'll call the gas constant. This has been computed experimentally for a number of things and found to be 0.082058 liter atmosphere per mole Kelvin. And so that definitely you want to have written down. The ideal gas law is on the top. That's PV equals nRT. P is pressure, V is volume, N number of moles, R the gas constant, and T temperature. So these types of problems you would be given all but one of the unknowns, all but one of the variables and asked to solve. So, say volume, number of moles, and temperature, and asked to solve for pressure, for example. So when you're looking at these problems, again, the first step you want is to identify what type of problem it is. Is it something where you're given a set of initial and final conditions, because then you'd use one of those three relationships we looked at just previously, or as an example where you're given a pressure, a volume, and a number of moles, and then asked for a temperature, in which case you use the ideal gas law. Another thing to note here where in the problem, if it says that it's occurring at standard temperature and pressure, that's also known as STP conditions. Those are where the temperature is 0 degrees or 273 Kelvin, and in most cases you'll use the Kelvin because that's what R is in, the units of R. And pressure is 1 atmosphere. Again, atmospheres is what that R is in. Another note there, so that gas law constant has units of liter atmosphere per mole Kelvin. So it has the units for pressure, volume, temperature, and obviously number of moles. So you need to make sure that your pressure that you're using with this equation is in atmospheres, that your volume is in liters, and that your temperature is in Kelvin to be using this constant and to be able to get the appropriate answer. So here's an example. This is actually an example stating sort of another rule that we know. But so what's the volume of 1 mole of gas at STP? So here's how you would solve that type of ideal gas law equation. So we're looking for volume. They give us 1 mole, and they say at STP conditions. We now know that that means that it's at 273 Kelvin and 1 atmosphere from the definition of STP conditions. So if we put the R in and we solve, we end up with 22.414 liters. It turns out, if you look here, we're not even identifying which type of gas, just what's the volume. It turns out that this is actually a relationship that you should know, that 1 mole of any gas at standard temperature and pressure is equal to 22.414 liters, or its volume will be 22.414 liters. So that's a constant value that is known. So the volume of 1 mole of gas at standard temperature and pressure is always 22.414 liters, irregardless of which gas you're talking about. Here's one with being able to use these in stoichiometric relationships, just as you've done before. Now here we're dealing with pressures and temperatures and a formula. So the reaction used in the deployment of automobile airbags is the high temperature decomposition of sodium azide to produce nitrogen gas. How many liters of nitrogen gas at 1.185 atmospheres and 30 degrees Celsius are produced by decomposition of 45 grams of sodium azide? Okay, so the first thing we know is we're given 45 grams of sodium azide. So we can convert that 45 grams of sodium azide to moles of sodium azide. Use the moles of sodium azide to figure out the moles of nitrogen gas that we'll produce. And so we'll know the number of moles of nitrogen gas we produce. They gave us the pressure, they gave us the temperature, and they're asking us for the volume. So we can use PV equals nRT to then solve for volume. So again, first figuring out the moles of nitrogen produced, we take the mass of sodium azide, convert that to moles, that's the first conversion factor here. And then we take the molar ratio from the balanced chemical equation that said that 3 moles of nitrogen gas are going to be produced from 2 moles of sodium azide. That gives us 1.04 moles of nitrogen gas. And then we rearrange the PV equals nRT formula to solve for volume. We have 1.04 moles of nitrogen. Sorry about that. So you have the 1.04 moles of nitrogen, the R value 0.082058, that's your gas law constant. The 303.2 Kelvin came from the fact they told you it was 30 degrees, so you have to convert that to Kelvin. So there's the 303.2 Kelvin, and divided by the pressure of 1.15 atmospheres, and you get 22.5 liters. That should make sense, that volume, because I remember I told you that at STP conditions, if we have a mole of gas, it's 22.4 liters. So these aren't exactly STP conditions, but they're close, and we have close to 1 mole. So in terms of like a ballpark answer here, this makes sense. I don't have a lot of problems in this particular slide set, so I would encourage you to use the problems that are in the text, as well as the pre-class and homework problems. And certainly, if any of those pre-class problems, you have any questions, be sure to ask those in class, or the homework for that matter too. So next concept here is partial pressure and Dalton's law. Dalton's law tells us that we can essentially sum the pressures of the mixture of gases and to get a total pressure. It's really just a definition of how we can sum. So we can take the partial pressures of the gases and add them up, and that would give us the total pressure exerted by the mixture. And you can see it written here, just that P total equals the partial pressures of all of the individual gases summed together. So if you're given, say, 2 pressures of a gas and a total gas pressure, they might ask you to calculate the pressure of a third unknown, okay, in which case you're just sort of adding the first 2, subtracting that from the total and seeing what's left. The other concept that goes along with this is the idea of mole fraction. Mole fraction is defined as moles of a component over total moles. It's really just the definition of a fraction with using moles. So one way to do that is the first one you see over here. So this little x sub I is that mole fraction, where we have moles of some compound I divided by the total moles in our solution. We can also use this. The derivation is not shown, but it's also known that we can also calculate a mole fraction by using a partial pressure of a gas and dividing that by the total pressure of the mixture. So this is another application where you could be asked to calculate a mole fraction, be given a partial pressure, say, of oxygen, and then total pressure of the mixture, and you can calculate it that way. These are the main components of what we know about the kinetic molecular theory of gases. So we know that they consist of tiny particles, that they move about at random, that we assume that the volume of the particles themselves is negligible compared to the total volume of the gas. It turns out that sometimes this does matter, so I'll talk a little bit about that in a minute. Most of the volume of a gas is empty space. The gas particles act independently of one another. There's no attractive or repulsive forces between the particles. Collisions of the gas particles, either with other particles or with walls of the container, are elastic, meaning they bounce off. And the average kinetic energy of the gas particles is proportional to the temperature, which is just a restatement of one of the laws. And this just illustrates some of those things. There's a relationship between the molecular weight of a gas and the relative average speed of that gas. So what you can see on this chart here is as the molar mass increases, the average speed goes down. So hydrogen gas's average speed is 1,960. Its molar mass is 2. Whereas if you look over on the right, carbon dioxide's molar mass is 44, yet its average speed is only 415, and you can see that general trend. And we now know that that's a proportional relationship, and I'm going to come back to this, that that speed or rate of effusion, and I'll come back to what effusion is in a moment, is equivalent to 1 over the square root of the molecular weight for the gas. So this is something that you should be able to calculate. So the rate of effusion of a gas is 1 over the square root of its molecular weight. So then you're asking, well, what is effusion? So we'll go back to this one. Diffusion you've probably heard of before. So diffusion is the mixing of gas molecules by random motion under a condition where those collisions can occur. And you can see here that's just sort of showing there's a space that the gas 1 and gas 2 can cross over and mix, and if you leave it for a certain amount of time, what you'll end up seeing is an equilibrium between the gas particles of 1 and 2 on each side of that opening. Effusion is the escape of a gas through a pinhole into a vacuum without molecular collisions, and this is what we can actually, we can measure the speed, and this is the speed that I was talking about is equivalent to 1 over the square root of the molecular weight of the gas. So it's one way to measure the speed of a gas, so that's why we use this rate of effusion in order to sort of compare speeds of gases in combination, or sorry, relative to each other. We use this relationship. So again, it's fairly simple. The rate's proportional to 1 over the square root of the molecular weight. I think, don't know if your text, right, your text also gives you another important formula that's not shown here. So on page 338, Graham's law, under Graham's law, it says rate of effusion is 1 over the square root of its mass or molecular weight. Right below that is actually something you should know how to use, and that's how to compare the rates of two gases to each other. So the rate of gas 1 divided by the rate of gas 2 is equivalent to the square root of the molecular weight of gas 2 on the top divided by the square root of the molecular weight of gas 1 on the bottom, because recall the rate is inversely proportional, so that's why you see them reversed there. Another way to show that is just the square root over the whole thing, taking the molecular weight of 2 and dividing it by the molecular weight of 1. That's just a mathematical way to rearrange that. But do make sure you have that relationship down. It's about, I don't know, 3/4 of the way down on page 338, because that will allow you to compare the rates of two gases, which is a type of problem that you'll be given. And that type of problem, actually, is given in worked example 9.10 on the next page on 339. So you can use that to kind of check your understanding of that. I mentioned before that this is called an ideal gas law equation. Ideal because we're making some assumptions about gases which aren't actually always true. So what I'm going to do here is talk just a couple of the exceptions that we sometimes see. So you'll see the title here is Behavior of Real Gases. And we have calculated a different version of the ideal gas law equation that accounts for most of those differences that we see. I'm not going to ask that you use that alternative equation, but just that you understand that we do know that there are some exceptions to the behavior of ideal gases, and that we've accounted for them in a new type of formula. Okay, so one thing that we know is that a volume of a real gas is usually larger than predicted by the ideal gas law. We also know that attractive forces between particles, there are some, and that become more important at higher pressures. And so, again, those are sort of two examples, and we account for those intermolecular attractions and for that increase in volume by two separate variables labeled A and B in this overall equation known as the van der Waals equation. So this just sort of resolves the things that we know that real gases, the behavior of real gases, into a new formula. Again, I'm not going to ask that you use this formula, but just that you're aware that it does exist and sort of why. This last part I won't get too much into, but this just gives you some information about the Earth's atmosphere and a little bit about the depletion of the ozone layer, which I'm sure you have all heard of. So we'll stop there.